Okay, can you see my screen now?
Yes, yes.
Yep, thank you. This is the presentation for the paper named Crystal Privacy Preserving Distributed Representation Management. Okay, so we can go to the motivation of this paper. Imagine you have just arrived airport, a new area for you, and you don't have any internet connection. You did not activate your new SIM card, and you want to retrieve some urgent information. For example, you want to ask which is the best money exchange agency at the airport. So you need to ask people around you, and this is the situation we want to investigate. That means um, there exists the unshared internet in a specific area while the user in their needs instant advice from the others nearby. Okay, and the approach is using the peer-to-peer network. Um, but however, not all of the recommendations are reliable. So we need to have a method to decide whether we should believe on the recommendation or not. And some other privacy problems emerge in this situation. We can discuss this in both sides of the situation, the requester and the commander. So our solution is use a crystal. That is a security model for the for managing the distributing reputation score and for preserving a user privacy. Okay, this is the figure about the P2P communication among the nodes. For example, you can see in this picture, U1, that means user 1 is a requester. That means the user want to ask something. And the other nodes, for example, U0 and U2, etc. So that is the advisor. They give the recommendation. And of course, their solution or their answers should be corresponding with a score. That means the reputation score. Okay, so in this network, after the requester receives the answer from the advisors, they can evaluate the reputation and update the reputation of the advisor. That is the main idea about this paper. Okay, this is the details, the technical details about the reputation computing. First of all, you can see in this the first formula, this is the reputation score. That is actually the average of the reputation score from other user. Okay, this is for one particular user U, and this is the other user. We can construct a thing called the reputation score tuple, and this is have 4 fields. Okay, the reputation score that's the user U. Okay, evaluates and negative to other user. Okay, and the user U evaluates positive for other user. This is in the other direction. So this is the other user evaluates negative for this user, and this is the other user evaluates positive for this user. We can also use another function to compute the reputation level. For example, if you can see the RU taking from the first formula, it is in between the L1 and L2. Okay, that is the some threshold in the lower level. So we can consider it as low. So in the other range, so you can consider it as average. And in this range, we can consider it as high. So this is the representation level. The details of this computing you can see in the algorithm 1 and algorithm 2, which is used for the evaluation representation, and you use the algorithm 2 to compute the representation. So I don't want to focus in the technical details of these algorithms because it's very complicated. So we can move on to see how the solution works. Okay, and this is the privacy requirement for the network. In our models, we need to focus on the privacy requirements, and there is two aspects of the requirement. The first of all is the non-violated representation scores against the requester. And the second aspect is about the representation score integrities against the advisor. Okay, so that means we need to guarantee the privacy for both the requester and the advisor also. In the first aspect, it is to focus on the requester in case they try to learn the representation score received from the advisor, and the requester V can misuse the received representation score of use, for example, impersonating the owner received representation score. So we need to protect the representation score computation. In the second aspect, the privacy issue focus on the advisor U in the case that they codify their representation scores before sending them to the requester V. So we need to have a solution to check if the received representation score is integrity or not. It is a scheme of the homomorphic elliptic curve cryptography we use in our paper. For example, this is Alice and this is Bob. Alice have the private keys and the shared public key. Okay, so the public key is public, so that means Bob also have the public key, and Bob want to send the the message to Alice. Okay, so he can use the scheme of the encryption like this. Okay, this is an encryption using the public key, the shared public key KB, and M is a message as the input parameter. So, okay, this is the encryption scheme, and he sent on the encrypted information to Alice with the private key, so Alice can decrypt the encryption information, and there is only Alice can do this thing because Alice is the only one who have the private key. So in the description scheme, so you can see this is M, and okay, this is plus mean exclusive OR. Huh? So that means when we have this thing and this thing is so it will be eliminated. So we only have M left. That means we can decrypt the original message from Bob. The encryption private crystal protocols. So for the first privacy issues caused by the dishonest requester, so that means in the first aspect of the privacy problems. So we need to use some operators and as well as the comparative operator, the agglutinative operator and the comparative operator to calculate or to compare the representation score without review it. So for example, this is the plus and minus, multiply and divide. So in the the comparative operator, so you can compare this is less than or greater than or less or equal or greater or equal or different. So this thing can be performed without decrypting the information. So this is the way how we can protect the information for the user. In the second aspect, that means we need to guarantee the integrity against the dishonest advisor. So we can adopt the mechanism of the digital signature, and we use elliptic curve digital signature algorithm, ECDSA. Okay, this is the way how to use it. All right, and for the experiments, in the experiment, we use the PC of a Windows 10 Professional and 8 GB RAM, CPU i7 1.8 GHz, and we use some parameter of the algorithm ECDSA and pi with different key size. Okay, this is the different key size we can use in these experiments, and each value in the experiment is the average of 20 execution times. This is the result you can see in this one. So we have the combination of the case of SHA2 and ECDSA. So this is we have 8 cases, and in each cases we take the experiment for 8 sub cases for ECC with different key size and barrier with different key size. So you can see this one. So barrier it takes more time than ECC. And the experiment for the data lot we can see also in this picture. Okay, so to conclude the paper, so in this paper we investigate a scenario to offer decentralized closed area where the users cannot access the internet, and propose a privacy preserving protocol supporting the requesting user to evaluate the reputation level of an advising user before following his recommendation. The proposed presentation, the proposal presents the secure process of the reputation evaluation and computation against the privacy violation of the requester and the advisor in both aspects. And the future work, we will focus on the authentication issues of the nodes, as well as the privacy issues against the crystal server. Okay, this is some of our reference. Thank you. Do you have any questions?